So we begin by looking at the exponential function, and once we understand it a little bit, we will continue on with the logarithmic function. So let's start with the derivative of the exponential function. Here it states that the derivative of e to the x is, and there is no mistake, there is no typo here, it is e to the x, which is a very surprising result. The derivative of e to the x is e to the x. Think about it. Which other function that you know has its own derivative? The only other function that I know is 0. Derivative of 0 is 0. So this is a very unique function, and this is the reason why base e is called the natural base. Because as we're going to see later on in this video, if you were differentiating something like any other base, say 2 to the x, that turns out to have a derivative of 2 to the x times natural log of 2. But when you have e to the x, it turns out to be e to the x times natural log of e, but because that's 1, it doesn't even show up in the final answer. Therefore, when you take derivatives, it's easiest to work with the base of e. There's nothing extra like you would have with other bases. And what if you don't have just an x, but you have a function of x, something like u? The derivative of e to the u is e to the u times du dx. Now, where does du dx come from? That one comes from the chain rule, right? So you apply the regular rule, and then you multiply everything with the derivative of the inside. Here, because your function is e to the x function, if you have something like e to the x squared, this is considered to be the inside part of your e to the x function. So you multiply everything by the derivative of the inside. So let's do some examples with that. If your function is e to the x squared plus 1, its derivative dy dx, also known as y prime, will equal e to the same power times the derivative of the power. That's where du dx is telling us. And the derivative of the power is 2x. And typically we would write this as 2x up front times e to the x squared plus 1. Notice how this is different than the regular power rule. The regular power rule we had seen previously was something like, okay, so if you have u to the n, the derivative is n times u to the n minus 1. And then you could have times u prime if u is a function of x. Here we don't do that. We don't subtract 1 from the power because it's very different. See, in the past we had something like this, say x to the third power. So the power was a fixed number. When you differentiate that, that one becomes 3 times x squared. But when you're differentiating something like e to the x, it's a complete different function. The top is no longer a fixed number. So this rule no longer works. We need another rule, and that rule was given to us at the top of this page. So I just want to show you that so that we're not confused by the other rule. That rule only works when you have a fixed power and a variable base. Okay, moving along to the next few examples. Say y equals e to the 2x. What will be the derivative there? dy dx, or y prime equals e to the same power times the derivative of the power. In other words, the answer is 2 times e to the 2x. Okay, the next example. Okay, what we have here is a constant times a function. We don't need to apply the product rule there, right? The only time when you need to apply the product rule is if you have two things being multiplied where both of them have the variable. This one is like 7 times a function. The 7 remains. You just differentiate the function. Okay, think of this as e to the u, and the derivative will be e to the same power times the derivative of the power. And what is the derivative of 4 tangent x? It will be 4 secant square of x. and 4 times 7 is 28. So bringing the secant square up front times e to the 4 tangent x. So that'll be our final answer on that one. What about number 4? So there we're going to need the product rule, right? Because you have x times another function of x, e to the 3x. So let's use the product rule there. So y prime equals, okay, there I'm going to write the first one as it is, multiplied by the derivative of the second one, which is 3e to the 3x, plus, write the second one as it is, times derivative of x, which is 1. And I can take out an e to the 3x, and that will leave me with a 3x plus 1 as the final answer. Okay, and next we're going to take a look at the derivative of the natural log function. But before we do that, I'd like to take a quick look at the proof of the derivative of e to the x, because here I gave you guys a very important rule. But first I want to do some examples. Now that we've done that, I'd like to give you some reason, some explanation behind where does this rule come from? Why is the derivative of e to the x equal to e to the x? And anytime you have no idea what you're doing, you have no idea what the derivative of something is, you will go back to the definition. So the definition of the derivative of a function is limit as h goes to 0, or as delta x goes to 0, I just use h as you know, f of x plus h. So this is our function f of x. The original function is the e to the x function. So that is our f of x. So what is our f of x plus h then? Take every x out of that function and replace it with x plus h. That's what you will see here. E to the x plus h minus the function itself, everything divided by h. So f of x plus h minus f of x over h. Now this part right here, e to the x plus h, we can write it as e to the x times e to the h. Think about it. If you multiply them, you would have to add the exponents, right? And because this one has an e to the x and this one has an e to the x, you can factor it out in the next step. And you would be left with this. And this inner part, e to the h minus 1 over h, we can actually show that the limit of that as h goes to 0 is 1. You can even do an exploration about that on the calculator and just plug that into your, instead of h, you can plug in just x, like e to the h minus 1 over h, but instead of h, I use x, so it's easy to enter to the calculator. And pick some values as h goes to 0, and you'll be able to show that the y values are approaching towards 1. And that gives us an idea that this limit might be equal to 1. And again, there can be a more rigorous proof for that, but at the moment I'm just going to give you an intuitive understanding of what's happening here. So if that quantity goes to 1, so you have now e to the x times 1, which is as h goes to 0, this doesn't depend on h, therefore the answer is going to be just simply e to the x. So what we have shown is that the derivative of e to the x is e to the x, and that was the rule I gave you in the first place. Moving on to the logarithmic functions. So let's first take a look at what the rule says. We'll do some examples, and then we'll come back and try to understand where the rule comes from. We're going to take a look at a quick proof of this rule. So the rule says the derivative of the natural log function equals, if it's natural log of x, it will be simply 1 over x. Another surprising result in my opinion, because notice natural log completely disappears in the answer. Like if you think about it, the derivative of x squared, you know, a polynomial function, was another type of a polynomial function. The derivative of sine x turned out to be cosine x, a trig function, which is another trig function, right? E to the x, another exponential function e to the x, but here we start with natural log. Somehow its derivative has no natural log in it. We just lose it. So that's a very interesting property. And what if you have u? So if we have u that is a function of x, something like x squared, then the rule becomes 1 over u times du dx. And again, this times du dx comes from the chain rule. If it was just x, derivative of x with respect to x is 1. It doesn't even show itself over here. But if it was an x squared, you would have an extra factor of 2x, which is the derivative of x squared. Put it another way, 1 over u times u prime. You might also see that in some books written as simply u prime divided by u. So that's the derivative of natural log of u with respect to x. Now let's do a few examples. Let's differentiate this function. The derivative will be 1 over u times u prime. What is the derivative of the inner portion, the inner function here? 6x. Derivative of 5 is 0, right? So we just get 6x. And you could certainly rewrite this as a single fraction. 6x divided by 3x squared plus 5. Okay, how can we do the next one? Now, of course, we could apply the same rule, 1 over u times u prime, but the nice thing about the logarithmic functions is that if you can simplify it first, you're going to save yourselves a lot of time later on. Like, for instance, can we simplify this? So not y prime, but I'm going to write y one more time, but in simplified form. Okay, square root means 1/2 power, right? And property number 3 about logs tells us you can bring that power down. So I can write the same expression as 1/2 times natural log of 5x plus 7. Now I'm not subtracting 1 from the top power or anything because I did not differentiate this. You see, I just use a property of logs, specifically property number 3 that states ln of a to the r equals r times ln a. No derivatives involved there. So the power was 1/2. I wrote that down, and here I have a simplified version of the function. Now it will be easier to differentiate. The derivative equals 1/2 remains. Just differentiate this function. And we know what the rule is, right? 1 over u times du dx. So it's going to be 1 over 5x plus 7 times the derivative of the inside, which is 5. And if we clean it up a little bit, we can write this as 5 over 2 times quantity 5x plus 7. And you couldn't really simplify the 5 with this, with that, right? Because this is not doesn't have a factor of 5 that you could factor 5 out of that one also. So we're just going to leave it like this. Here's another example for you guys. Differentiate this function. Natural log of 7x plus 5 times quantity 2x plus 1 to the third power. And I gave you a hint on this one. I may not give you the hint on the test or in a quiz. So just always keep in mind, whenever you're differentiating the natural log function, the first thing you should try to do is always to simplify it first, because that will save you so much time. If you don't simplify it first, you do the 1 over u, but when you do the u prime, you're going to have to use the product rule. Within the product rule, you have to use the chain rule. It gets very messy. So if you can simplify this, in this situation, write it as a sum or difference of logs, and then differentiate. It's going to be so much easier. So I'm going to give you a moment to do that. Please pause the video and then come back in a little bit. Okay, I hope you had a chance to look over this problem and to try it on your own. And let's look at it together. the suggestion was to simplify it first. So if you apply properties of logs, you have log of a times b here. You should break it apart as a sum of two logs, and that power can also be brought down as a 3. Now it looks much easier, and it'll be so much easier to differentiate this. You don't need product rule anymore. Just differentiate each piece one at a time. 1 over u times u prime. So you apply that to the first part. The 3 remains. 1 over u times u prime. 3 times 2 is 6. And that's how we can leave the answer. Just like that. I know the book may also combine these and get a single fraction, but as far as I'm concerned, it would be okay to leave the answer like this. Here's another example, and once again, please take a moment to work this out on your own, and then come and check the answer, please. Y equals x times ln x. What is the derivative of this function? So here's the solution. Hopefully you gave it a try first. So we have to use the product rule this time, right? Because variable of you have the variable times something else involving the variable. So I wrote the first times derivative of the second plus the second times derivative of x, or 1. X times 1 over x can be simplified, and we're left with 1 plus ln x. A few more examples. Given f of x, can you determine f prime of 3? What is the derivative that is at the point x equals to 3? And also, another good example is given f of x equals x squared times ln x, find the equation of the tangent line to this function at x equals to 1, also at x equals to e as part B of the same problem. The hint, once again, is to simplify the natural log function first before you start differentiating it, because otherwise it's going to be very messy. Because otherwise you have to use the quotient rule, you also have to use the chain rule with this 1/2 power and the outside of everything. It would be so much easier to simplify it first. So try it and come back to check out the solution. So hopefully you did give it a try. And here's the solution. First of all, this power of square root or power of 1/2 can be brought down. Property number 3, right? Then natural log of a over b can be broken down as natural log of a minus natural log of b. Then we can simplify this, rather differentiate this with much ease now. No need for quotient rule, no need for power rule, just 1 over u times u prime. That's applied here and again here. And the only thing is this problem also wants us to know what is the derivative at the point 3. So at this point, plug in 3 everywhere you see an x, and you should be able to get this answer. And as for the second example, again, we start with the product rule. Then plug in 1 for x to get the slope. Plug in 1 into the original function to get the y, and get the equation of the tangent line by using the point 1, 0 and a slope of 1. And now I'd like to show you a very quick, very neat proof of where the derivative of ln x comes from. Again, we were surprised 1 over x was the answer. Where did that come from? Let me see if I can show you that really quick. This is like a 3-line or 2-line proof. Okay, we're trying to show derivative of ln x is 1 over x. First step, write e to the ln x equals x. Why is this true? Because e to the x and natural log of x, they're inverse functions of each other, and they will cancel each other. So we've seen this was one of the properties actually on the first page. They cancel each other and you get back x. So we know this is true. Okay? We also know how to differentiate the exponential function now. Think of this as e to the u. So if you differentiate both sides, differentiate this side, and you will have e to the same power times the derivative of the power. Differentiate the right-hand side, derivative of x is just 1, right? Okay, now remember what we're trying to solve. We're trying to solve the derivative of ln x. That's what we're trying to figure out. So let's divide both sides by this, because we want to solve for this quantity. So divide both sides by e to the ln x. In the next step, you will see I have 1 over e to the ln x, and on this side, it has disappeared. So these canceled, and here's what we have left. So derivative of ln x is this. But what do we know about e to the ln x once again? E to the ln x is x. So there we have it. Derivative of ln x is equal to 1 over x. So it's a really neat short proof, and it's anytime you can try to understand why a rule works, it's great because you'll have a better understanding of something, and hopefully it'll stick better. It'll go to your long-term memory if you can have an understanding as opposed to just memorizing a rule. So this one was a real easy proof to show derivative of ln x is equal to 1 over x. Okay, the only other thing left to do, okay, what do we do with different powers? So for example, say you have the derivative of a to the x. So far we have looked at e to the x, but what if you're doing derivative of exponential function to any base a? Now I'm going to leave this proof up here for those of you interested in theory to explore. At the moment I'm just going to go to the answer. And the answer is, if you have any other base, such as base a, the answer will be a to the x times ln a. But if you also have something like x squared or x to the third or any function of x, at the very end, you should also multiply this by the derivative of that as well. That comes from the chain rule. Okay? We'll just put dot, dot, dot there. But if it's just x, you don't have to worry about that part. So let's look at an example. As I gave you the preview earlier at the beginning of this presentation, for instance, derivative of 2 to the x. Any guesses? What about derivative of 5 to the x? By the same rule. But what if you have 2 to the sine x? So that would be, first you apply the same thing. But in addition, anytime you have something more than just x, you also need to multiply it with the derivative of that. So that will be multiply everything by cosine x. So in a sense, this is your generalized rule of a to the u is a to the u times natural log of a times u prime, or du dx. Now the good news is, I would say more than 95% of the time in calculus, you're going to see e to the x and not any other base. So I'm showing you this so that you can be familiar with it, but don't worry, I understand there's too many rules to remember, and this one is one. It doesn't come up very often, and you don't have to worry about it too much. And what about derivative of logarithm to any other base? We know derivative of ln x is 1 over x, but what about log base 10 or log base 2? What would be the derivative there? At the moment, we don't know that. Again, those of you who are interested can watch this proof, can look through the steps, and basically it relies on the change of base formula. We write this with a new base of e as ln x over ln a, and from there we're able to get the derivative. This becomes just a constant, and we know the derivative of ln x, so the answer turns out to be 1 over ln a times 1 over x. So for instance, for this question, if it was just ln x, it would be 1 over x, right? But because there's an extra 3, it turns out to be, based on this rule, 1 over ln of 3 times 1 over x. I would say this is also a more obscure formula. the ln function gets so much more use. Basically, any other base, these base 2 or 3 or 10, be familiar with these results, but if you need them on the test, I would provide you with the formula for those. And finally, something called logarithmic differentiation. And that, in a sense, has nothing to do with what we've been doing so far. In a way, look at this function. There is no natural log in here. There is no e to the x in here. But what we do is we introduce natural log ourselves. So I'm going to go through the solution relatively quickly. So if you have a variable base and a variable power, you can use logarithmic differentiation. And the way to do that is apply natural log to both sides, which I did. Bring the power down. That's the property of logs. Then you differentiate both sides. Because the way this stands, we really don't have a rule for it. If it was 3 to the x, there's a rule how to differentiate. X to the 3, there's a rule how to differentiate. But a variable to the variable base, we just don't know. So that's why we apply natural log to both sides. Then we differentiate. Differentiate both sides now with respect to x. Derivative of ln y with respect to x will be 1 over y times dy dx. And derivative of x times ln x, use the product rule there to get this. And ultimately, we want to solve what is dy dx. So that means you're going to need to multiply both sides by y. And that's how we leave the answer. And at the very end, we bring the y back in, place x to the x, since y was defined as x to the x at the beginning of our problem. So even though we didn't have a rule to do this problem, by applying natural log, taking the derivative after that step, we were able to find the derivative for a variable to a variable base, x to the x, which turns out to be this quantity. And one last thing I'd like to show you here is, this is another example of logarithmic differentiation. And in a situation where you have a very complicated function and you're trying to find the derivative, yes, you could use the product rule, you could use the quotient rule to begin with, and then within that, the product rule. Very, very messy. So a better approach is as follows. Once again, there is no logarithm here to begin with, right? So just like in the last example, we are going to introduce the logarithm. So apply natural log to both sides, which I did. Then we're going to use the property of logs that says you can break this apart as a sum or difference of logs. And so it's going to be log of this plus log of that minus log of this. And each of those powers can be brought down. The 4 is brought down, the 2 is brought down, the minus, because this was in the denominator, right? And I know I'm going through this last example relatively quickly, but when you get a chance, you can take a look at this more slowly and try to do it on your own even. So the next step is we're differentiating both sides. And now it's easier because there's no product, no quotient to worry about. First of all, natural log of f of x. Think of this as ln u. It's going to be 1 over u times u prime. Over here, again, 1 over u times u prime. Do it with all of the natural logs. And we're done. Technically, we're trying to find f prime. So multiply both sides by f of x, and we're done. And I also cleaned it up a little bit, like 4 times 3 is 12. And then f of x, I can put its equivalent in the next step. And I know it looks gigantic and, intimidating, such a long expression, but really all I did in the last step is replace this f of x by its equivalent from step number 1 times, we already had all that other stuff within the brackets, which I just copied down over here. So whatever the given function was, f, at the very end, we found f prime. There were maybe quite a few steps, but it wasn't, each step in itself was, I would say, elementary. The steps themselves were not that complicated. When I say not that complicated, in comparison to trying to use the product rule and the quotient rule, now that would have been messy and complicated, in my opinion. So this approach really helps when you have a quantity that you can apply natural log to break it apart. And at the end, when you differentiate, natural log disappears anyway. So there you have the derivative using an interesting approach. So I know there was a lot of stuff covered in this lesson. And to be more exact, I'll go back to the initial objectives that we had. We reviewed properties of logs, learned the derivative of exponential function to the base e, natural log, derivative of natural log function, and then derivatives of exponential and log functions to any base. And then we concluded the lesson with something called logarithmic differentiation. So, like I said, there's a lot covered here, but I know if you can go to your group activities right now and to your WebAssign homework assignments, with practice, I know you're going to master this, and it's not going to be as bad as it originally appears, I'm sure. So good luck with studying this material.